Resume recording. Well, good morning. My plan today is to cover 1.4. My impressions are it's fairly straightforward with a couple, tricky things to watch out for, and then actually try to start 1.5. You may have noticed in our schedule, 1.5 and 1.6 are both scheduled tomorrow. Those are the two sections that have to do with fractions. So if I can get 1.5 started, it just gives us more time tomorrow to deal with adding and subtracting fractions, which is usually the more challenging part of that. So I just wanted to close part of that window there. Okay, so that's my plan. But as always, I would say, let me start. Anybody having trouble? Look, I see most of you guys are getting through 1.3. Some of you have even started work your way through 1.4. Good job, Tara. So anyway, speak up. Let me know if you're having issues with anything, some of the concepts that we've covered so far, okay? So just chime in. But if nothing else, I'll get us going. So we've been dealing, I guess since yesterday, with our expanded set of numbers we call integers, the whole numbers and their opposites. Notice I try to avoid saying positive and negative whole numbers. Technically, there aren't negative whole numbers. The whole numbers are just the positives, and their opposites are the others. And they go together to make that set called integers. And we added and subtracted those integers yesterday, dealing with subtracting a negative. Sometimes the most challenging part there turns into addition. Multiplication and division of integers follow a couple nice rules. And I just kind of present it like this, in parentheses, if you're multiplying or if you're dividing two positive numbers, right? 10 divided by 2, you get a positive result. So this is just supposed to indicate that positive, positive, you get a positive result. Same with division. If you're multiplying two negatives, basically saying, I want to find the opposite of that opposite, it turns into a positive. And the same applies for division. If you divide a negative number by a negative number, it's still kind of asking in a way that we'll talk about a little more with fractions, I think, but we're finding the opposite of the opposite. And again, it turns positive. So the result, if the signs are the same, your result is going to be a positive number. If your signs are different, the result is a negative number. And that's the same whether you're positive divided by negative or negative divided by positive, you get a negative result. If the signs are different, your result will be a negative number. If the signs are the same, your result will be a positive number. There, now you know. That's the what I call the straightforward rule about multiplying and dividing integers, positive or signed numbers, positive and negative numbers. Same signs positive, different signs negative. So, you know, we can say, well, okay, what about -4 times -6 times -3? How can I make this any trickier, you know? Well, here we actually have 3 numbers in a row multiplied together. And, you know, in reality, we kind of do one thing at a time. I multiply maybe 2 of them together, and then I do the 3rd step. Thinking of it that way, I just look at multiplying those 2 numbers together. 6 times 4, I would get a 24. And because those 2 are negative times negative, that will be a positive 24. But then I still have times -3. So now I have positive times negative, which means my result will be a negative number, and that happens to be 72. 3 times 24, 72. What can we kind of draw or infer from this? If I have an odd number of negative signs, right? Every pair turns positive, but then I have an odd one out that turns it negative again. If I have an odd number of negative signs, I'm going to get a negative number. The board is banging around this morning. Let's see. If I have a string of multiplications and, don't get too fancy here, Steve. If I have a string of multiplications and they're all positives, well, it's just positive times positive. Or actually, what I was trying to get at is if I have an even number, an even number of factors and they all happen to be negative, well, excuse me, those 2 are going to turn positive and those 2 are going to turn positive. My result is positive. What's different? My board's banging around today. So an odd number of negative signs results in a negative number. An even number of negative signs results in a positive number. Okay. Whoop. And two to the 4th. Here's an exponential expression. The base 2 uses a factor 4 times. Excuse me, a little congestion this morning. 2 times 2 times 2 times 2. Careful, it's not 2 times 4, being an 8. It's 4, 8, 16. This turns into the number 16. Well, what happens if I start seeing some negative signs in that expression? Well, if I want to use the number -2 as a base, and then I'm going to put an exponent on it, I have to wrap up that -2 in parentheses to say the negative sign is part of the base that I am now going to put an exponent on. All right. So this is -2 as a factor 4 times in a row, an even number of negative signs. This result will be positive. You know, there's those two make a positive, those two make a positive. This result is positive 16. Okay, big deal. Where's the wrinkle? What if I do this? Yeah, making it, not writing it very nicely. -2 to the 4th. This is sort of the big, you know, the tricky little spot here in this section. Notice the difference. That negative sign is not inside parentheses. It means it's outside of the base. It's outside the base. It's not, the negative sign is not part of what is being raised to the 4th power. This would almost be clearer if I'd said, oh, that's the opposite of 2 to the 4th. So this is really saying find 2 to the 4th and then find the opposite of it. So this one, we know it's going to be a 16, but this one is -16. So you're going to see this as, you know, kind of question. Often these two are side by side. You know, what's the difference? Well, here the negative is part of what you're multiplying, and here it's not. You apply it, in a sense, after you've done all the other multiplying. That makes the most difference when your exponent is a positive number. In this case, you get a positive result. In this case, you get a negative result. Now, if my exponent was a negative number, it tends to turn out negative but for different reasons. They both have the same answer. Let's say I do 4 cubed. All right, well, that's 4 times 4 is 16 times another 4 is 64. I do this a lot, so I know those numbers. Don't worry about it. Now, if I do -4 cubed, like that last example, that negative sign is part of the base. That means I have -4 multiplied times itself 3 times. I have an odd number of negative signs there. That's going to be a negative number. That one is -64 because of that odd number of negative signs. If I write the negative or opposite of 4 cubed, I'm going to get the same number because it's just saying take this 64 and now make it opposite, make it negative. So with that negative exponent on there, those two give me, here's where I say, you get the same answer, but for a different reason. This is because an odd number of negatives were multiplied, and this was because we're choosing to switch it at the end. So that distinction really makes the most difference when you have an even exponent there. You got to watch out for that. Okay, so that's kind of the big deal about watching out in multiplying with negative numbers and exponents. Of course, we throw in some order of operations problems. Make my dots bigger here. I noticed that again, even after we talked about it, was it yesterday? My next example, I didn't make them big. Surprised, just double check, and nobody else looks like they're trying to join us right now. Yeah, just a string of different operations. An expression again, notice nothing we've been dealing with so far really asks us to equal something else. You know, we might sometimes say, I might sometimes say, okay, all of this equals something at the end, but we're not trying to solve an equation. We're still simplifying expressions. All right, so here looking at this, I'm talking about GEMDAS, right? Grouping, exponents, multiply, divide, add, subtract. Are there any groupings, real groupings? These parentheses, You might say, unfortunately, we use parentheses for lots of different things. You gotta kind of recognize the context. These parentheses are just containing those negative signs. So it's not technically a grouping saying we have to do that first. So I'd skip the grouping step. There's no real groupings. Are there any exponents in this expression? Nope. Well, then we're down to multiplications and divisions. Well, here's a division and here's a multiplication. They're kind of separated by that addition in the middle there. So we can kind of do those both at the same time, at the same step, you might say, this next step. So here I have a negative divided by a positive. So I'm going to get a -9. Here's that plus sign. And here's a multiplication. Negative times negative, I'm going to get +30. So now I'm just down to an add subtract step. A -9 and add 30. Their difference is 21, and the positive is bigger. So that'll be +21. What result there? So just some order of operations problems that we'll, throw at you, ask you to practice. Okay. And how about some evaluation problems? Here's my expression, negative of x plus 2. And we're going to evaluate this expression if an x is a 6 or if an x is a -6. So making two problems out of one. So we just take that number and substitute it in for the x, replace the x. So if x is a 6, I'm going to get negative of, or opposite of 6 plus 2. -6 plus 2, -4. Okay. Or if x is a -6, here's the trickier one. If x is itself a negative number, I want the opposite of -6. Notice I had to use some parentheses to keep those negative signs separate, and plus a 2. So this is the opposite of a negative, makes that +6. And I'm going to get +8 out of that. There's an evaluation problem where that negative outside affects what you put in for the variable. It makes a difference whether it was positive or negative to begin with. Quite a different result. A couple more of those I have here on my list. How about this one? I think there was something very similar to this in one of the My Open Math problems. Here's an expression, x plus y, and that entire expression is squared. And let's say that x is a -15 and y 29. Looks like big numbers, but it doesn't turn out too badly. All right, so I'm going to evaluate this expression. I'm just going to plug the two values in for the x and the y. So here's my parentheses. -15 plus a 29, that whatever result I get inside that grouping, I am then going to square. So -15 plus 29 is a +14. Now I don't really even need parentheses anymore because it's all combined. I can just say now that's 14 squared. Okay, 14 squared, 196. Okay. Let's see. What if I had, I'm going to erase that one, okay? Can I make it more interesting? Check my example. Whoops. Well, let's say, what if that was a 3? I'm going to cube this one, change a couple numbers here. Well, what if this is 8 and this is -10? Okay, Those are the values I'm going to plug in. Again, this expression has the exponent on the outside, so I'm going to simplify inside first. And this becomes 8 plus, I'm going to use extra parentheses here. You can do it neatly like that. You don't need brackets, but for that negative sign. So I didn't have plus minus right next to each other. So, oops, don't lose my exponent. Combining those, 8 basically minus 10 is going to give me a negative 2. Here I need those parentheses after combining to wrap up that negative sign inside before I put that exponent out there. Now for my previous explanations, because it's an odd exponent, we're going to get that negative number anyway. But if that had been an even exponent, like, that really would make a difference whether that negative sign was inside or not. So that's 2 cubed with a minus sign, negative 8. Check yourself if that's confusing. Didn't get that. All right. So that's kind of it, I think, for 1.4. Multiplying, if you can remember those basic rules, same sign is going to be positive. Opposite signs are going to give you a negative. Watch out for those exponential expressions. Is the negative sign part of the base or not? Is it outside? I sometimes say, you know, the exponent's only attached to the closest expression. That exponent's only affecting the 5, not the parenthesis, not the negative. This exponent, the closest expression, is everything in the parentheses. So the parenthesis is part of the squaring there. Negative 25, positive 25. Kind of the catch problem in this little section. Watch out for those. If that's okay with you, I'm going to change gears and start 1.5. All right, getting into some fractions. There we go. Slow me down or interrupt, ask questions, you know, usual. Shuffle my papers. All right, fractions. Fractions are that notational device where you have, basically that's a representation of it can be a division problem or represents parts of a whole, that top and bottom, numerator on top, denominator on the bottom. Somehow you have to figure out how to remember that, right? 1.6 deals with adding and subtracting fractions. That's where it tends to be the slightly more complicated section where we have to get the common denominator, that kind of thing. 1.5 is going to just introduce fractions, and we'll do some multiplying and dividing of fractions. So a fraction can be thought of as a part of a whole. If I take a whole object represented by that circle, and I divide it up into, those are clearly all equal sized pieces, right? Divide it up into equal sized pieces. Any one of them is one part out of how many pieces I made. So this is 1 out of 4. So that shaded part represents 1/4 of the whole. One part out of how many pieces did you cut it up into, right? If you're not that big a pizza eater, you know, maybe I've cut it up, terrible size pieces, but they're supposed to look like they're the same size, right? So here, how many pieces did I cut it up into? 6 equal sized pieces. Pardon my drawing. So that represents 1 out of 6, 1/6. Okay. Now, what if I say take my first drawing here, and I'm concerned with, so next thing I'm moving right into our concept of equivalent fractions. Two different looking fractions that represent the same value or quantity. So here, I still have my circle cut into fourths, and I've identified 2 of those fourths. But we also can kind of visually see that's the same as half of that circle. Somehow 2/4 and 1/2 are equal to each other, and we'll get into the detail real quickly here. You've probably been there, but I got to touch base on everything, right? Similarly, let's say I take my circle of 6, and what if I have 2 of those 6ths, right? 2 of those 6. Now it's not quite so obvious from that drawing in particular, but maybe you can see 2, 2, 2, that's the same as 1/3. So those 2 fractions represent the same value. They are equivalent fractions, even though they kind of look different. Similarly, these are called equivalent fractions. Well, you probably know the basis or the technique, but if I have a fraction, if I can multiply the top and the bottom of the fraction by the same number, then I've made, you might say, both sides of that fraction proportionally bigger, equally bigger, and I can build then an equivalent fraction. So for instance, if I take my 1/2 and I were to multiply both the top and the bottom by 2, I get the 2/4, which means 1/2 and 2/4 are equivalent. Similarly, if I took my 1/6 and I multiply, whoops, I'm working backwards. If I took my 1/3 and I multiplied the top and the bottom by 2, I get the 2/6. So 1/3 and 2/6 are equivalent because I've done what is a legal thing, multiplying both the top and the bottom by the same factor. So we want to be able to create equivalent fractions, especially when we start trying to combine them and build those things we're going to call common denominators. Next section, right? Adding and subtraction. We need common denominators. Well, all right, so equivalent fractions. Some of your homework problems, for instance, let's say, might say, find 3 different equivalent fractions for this 3/5. Well, just pick any numbers you want to multiply the top and the bottom by. I might say, okay, if I multiply both the top and bottom by 2, I'm going to get another equivalent fraction. I can multiply the top and the bottom by 7. I'm going to get an equivalent fraction. Or by anything you decide to multiply them both by. As long as you're doing the same to the top and bottom, you're going to get equivalent fractions. Now, those are all equivalent to each other. They just look different. They have proportionally larger values. So that leads us to going the other way around. Simplifying fractions. Well, we prefer, at least at the final step, I'll say this, almost always you will be asked to simplify your fractions, a concept called reduce to lowest terms. Well, reduce to lowest terms, what does that mean? Well, we want to get the smaller version, smallest numbers in there, 1/3 rather than the 2/6, if we can figure out how. So we kind of do that process backwards. Opposite of building up equivalent fractions, if I can recognize that my fraction, both numerator and denominator, have a common factor in them, that common factor actually looks like C/C is like the number 1. It's the same on top and bottom. It's a whole. So it actually cancels out and I get just the smaller number, the other numbers that were left. So if I have a fraction, and I'll do the long answer here, and you can just usually, if you're getting it, you can do it in your head. But if I recognize that both of those numbers have a factor of 2 in them, they have a common factor of 2, those 2 divided by 2 is the number 1. So I can cancel those out. We usually just kind of cross them off. And so that reduces to 3/4. 6/8 and 3/4 are equivalent fractions. I reduced, I went sort of, rather than making it bigger, I made it smaller. Again, similar. Well, here's a couple of big numbers. Maybe there's some common factor that I could use to reduce both of them. Gee, they're both even, so I know I can divide them both by 2's. So what this is 15 times 2, and this is 21 times 2. All right, so I could cancel out those 2's. Oh goody, I've got 15 over 21. Am I done? There's my loaded teacher question. Are there any more common factors? Oh, do you recognize they're both divisible by 3? Oh yeah, so I can take out a 3. Take out a 3 is kind of, we took out a 2. Take out a 3 is kind of the way I'm going to say it. So this is 5 times 3 over 7 times 3. Those 3's go away. 5/7 is really the lowest, the reduced factor there, lowest terms. Now, if I recognize that right from the start, oh, I could cancel 6 out of that and 6 out of that. You know, that's 5 times 6 and that's 7 times 6. Good for you. You know, fewer steps. If you can do that, you get there. It's kind of multiplication tables kind of coming back at you, you know, backwards there. How well do you know your math facts, your multiplication tables, right? So reducing to lowest terms, you'll almost always be asked to do that. I guess I'll say on a 10-point test question, working with fractions, and you get to a fraction answer, if you don't reduce it to lowest terms, you're probably going to lose a point. Okay, just straight up tell you that, you know, you were asked to reduce the lowest terms, and if you don't reduce it all the way, you know, you didn't quite get there. You got most of it, you got 90% of it, you didn't get that last part. Watch out for that sort of instruction. Some unusual ones here still. So now we're still talking about simplifying fractions, reducing the lowest terms. How am I doing time-wise? Good, good. Still nobody else trying to join us? That's fine. How about, if it just happens to be a negative fraction, that's fine. It's still going to be, we reduced the lowest terms. Looks like I can divide those both by 6. Now, I did the long answer where I actually broke out the factors so you can see them. What we folks often do is if you recognize that factor and you can kind of do it in your head, it's like, oh, if I divide this one by 6, I'm going to have a 1 left. We never really, we don't always show what we're dividing by as long as you're real careful about keeping track of these things. If I divide that by 6, I got a 2 left. Oh, so 1 over 2, and it was negative, stays negative. Okay, so this is kind of the shortcut notation folks will often use to reduce the lowest terms. You're still kind of showing indirectly what you did. Oh, I divided them both, and I got to those 2 numbers. So you can do that. Oh, let's see. What if I had this, what if that actually looked like 3 fractions in a row, right? That could have been 6 over 16 times 8 over 12 times 9 over 3. I can put all those numerator values together like they're in 1 fraction, and all those denominator values together like they're in 1 fraction. So here I have a string of multiplications, and I would like to simplify this fraction. Reduce the lowest terms. Now, I'd rather not multiply all these out and get a huge number and another huge number and then start working to make them smaller before you do the multiplying, even if it was just the 2 numbers side by side. Oh, I'm getting into multiplying here already. Oops. Come on, Steve, be careful. I'm going to do it anyway, and I'll back up if necessary. But here, I'm trying to reduce these fractions. I guess you can see I could reduce each one of those fractions individually, right? I could reduce each one. I could divide that by 2. I could divide those by 4. I could divide both those by 3s. I get smaller numbers before I multiply. I'm sorry, I think I need to back up. I did jump ahead of myself. I'm going to save this one, okay? I apologize for kind of going out of order on my own notes here. Yeah. Multiplying fractions. It's kind of built on, well, if I have two fractions multiplied together, all right, here's one fraction, whatever those numbers are, a over b and c over d. If I multiply them together, I simply multiply the numerator values together, AC, and multiply the denominator values together, BD. So if I have something like 2/3 times 5/7, and if I want to multiply those two together, I multiply the 2 times 5, and I'll get a 10. And I'll multiply the 3 times 7, and I'll get a 21. When we're multiplying or dividing, this will be the step where, now double check and make sure, is that in those terms? Well, I don't recognize any common factors. That's what I was trying to get at over here. So that's multiplying. Just multiply all the numbers that's on top together, multiply all the values in the denominator together, and you get what you get. Then look to see if there's some reducing you can do. Well, here's another one. I've got 3/7 times 14 over 6. And I, of course, made this up on purpose because I'm going to have to do some reducing to lowest terms after I'm done with this. Now, it's true, I can do, well, 3 times 14 is 42. 6 times 7 is 42. Oh, gee, 42 divided by 42. That's really going to turn out just to be the number 1. Well, that was just by chance. It reduced all the way to 1. But at this point, before I did the multiplying, if there is a common factor between the numerator and the denominator, we've already seen we want to reduce that. But it also works, like I was getting at a minute ago, that this is like one fraction with those 2 factors on top, 2 factors on the bottom. And I can cancel between this 3, that's that phrase, cancel, that sort of get rid of it. I can divide this 3 and that's 6. I can divide them both by 3. So before I multiply, it's often convenient to do that. So you work with smaller numbers at the end. So here, like, okay, I can divide that by 3 and there's a 1. I can divide that by 3 and that leaves a 2. Okay. Now, oh, look, there's 7s I could divide out of those 2 numbers. If I divide that by 7, I get a 1. Now, if I divide that by 7, I get a 2. And so now I've got 1 times 2 and 1 times 2. And maybe even at this step now, I would have recognized, oh, I have 2 over 2, and I could have just canceled those, but there I'm going to get my 1 again. So the point of this process is it sometimes saves you work at the end if you can recognize things to cancel before you do the multiplying and get the big numbers. Some examples for that, and just practice a little bit more. Yeah. Fourteen 15ths times 9/20ths. The TH is in there, right? Well, I can do 9 times 14, get a big number, and 15 times 20, get a big number, and then try to simplify. Can I recognize any common factors at this point? Well, nothing between those two. Nothing between those two. But how about the 14 and the 20 are both even? So if I can divide them both by 2. If I divide that by 2, it leaves me 7. Divide that by 2, it leaves me 10. So there I did that, canceling the 2. These are both divisible by 3. If I divide that by 3, I have a 5. Divide that by 3, I have a 3. Just looking at those little numbers, again, I don't see any more. So I'm ready to 3 times 7, 5 times 10, And just in case I missed it, I'll think again about that very last number. Is there still possibly some factor I didn't recognize yet? But no, they don't have any. This is strictly 2s and 5s, and that's 3s and 7s. Here's where your kind of prime factors can help out. I know what those numbers are built out of. So that was just another example of trying to cancel before I multiply. Those ideas are okay. I'm going to talk about some dividing. All right, switch gears a little bit. Dividing fractions. Whoops, your pen's wearing out. Not fractions, but 6 divided by 3. Oh, we know what that number is. But notice that is the same as 1/3 of 6. All right, so that's 6 times 1/3. Now 6 is like 6 over 1. They don't quite line up, but this is just a multiplication problem like I did a minute ago. 6 times 1, 1 times 3. Oh, and I get this. Now I'll reduce the lowest term, 6 over 3, and I'll get my 2. What's he getting at? All right. So this division was the same as multiplying by this number that somehow is sort of related to 3, right? It's upside down 3. That relationship between those numbers, they're referred to as reciprocals of each other. Reciprocals. Basically, it's like turn it upside down. So here, like here, I wrote, if I write 6 like a fraction, right? 6 over 1, 6 whole parts. It's reciprocal to flip it over. It's 1/6 because it's reciprocal. Kind of important relationship between those two, which comes in handy or very helpful, very important actually in equation solving. If you multiply those two together, they sort of cancel each other out and you get a 1. We'll see why that's important in the next chapter. But that's a feature of reciprocals. They kind of cancel each other out. All right, so what was I getting at is dividing by 3 was the same as multiplying by its reciprocal 1/3. That's what we basically do for fraction division. And here's sort of that abstract presentation again. Pen's going. All right, if I have a fraction divided by a fraction, we don't really divide directly. Here's like one of those things where I said the other day, mathematicians might say there's no such thing as subtraction. It's really just adding the opposite. Here mathematicians might say there's really no such thing as division. It's multiplying by the reciprocal. So this division problem is the same as flip over the 1 after the division sign, invert and multiply. You might have remembered that from grade school or something. Use the reciprocal of that 1 after the division sign and turn it into a multiplication problem. So we always turn division of fractions into multiplication. Three-fourths divided by 5/8. Don't try to do any canceling. You can't do that at this stage in a division problem. You need to turn it into a multiplication problem. Slow down, Steve. So that's the same as 3/4 times, flip over the second one, find the reciprocal, times 8/5. That's the reciprocal. Flip over, it's a fraction, you flip over the fraction. That's the reciprocal. Now I'm ready to multiply. Maybe you'll notice, oh, I could divide some 4s out of here right now. Save me some work later. 2 times 3 is 6. 1 times 5 is 5. And double check, that's lowest terms. So that's the big deal really about dividing, is you have to turn it into a multiplication problem. So here I purposely wrote one that looks like a fraction divided by a whole number. 16ths divided by 21. Well, we have a fraction divided by some other number. We want to turn this into a multiplication problem because we're dealing with fractions. Way to get that started is to just think of this as a fraction over 1. Right? Whole numbers can always be thought of as that whole number value divided by 1. So now I can turn this into 7/16 times reciprocal now is 1 over 21. Okay, so I just took 21 and I flipped it over, made the reciprocal. And I'm ready to multiply, but gee, I noticed some, I made it up, so there's something I can cancel here. I can divide some 7s, and I got a 1 over 3 times 6 is 18, that's 48, okay. 1/48. Invert and multiply was that elementary school phrase, you know, for dividing fractions. If you remember that idea. All right, and fraction divided by fraction. What's the sign of my simplified answer going to be? Positive divided by negative. That's just part of the thing to catch in this problem. It will be a negative number. Okay. But I want to turn it into a multiplication problem. So this is 5/18 times, still using the parentheses just because of that negative sign. Flip it over, 24 over 15. Now I'm going to look, see if there's anything I can do some canceling. Doesn't matter, that's negative. I can still divide both those numbers by 5. And let's see, 18 and 24, nice common factor. Obviously 2s, but how about 6s? You know, think of the biggest one you can think of. If I divide by 6 and divide by 6, okay, don't lose your negative sign. Unfortunately, you've got something that happens. So I'm going to multiply now. 1, use your little numbers, right? 1 times 4 is 4. 3 times 3 is 9. And remember, put your negative out there. All right. So here's a good time for me to just talk about negative signs with fractions. This is a division problem, right? 3 divided by 4. And if it happens to be a negative 3/4, well, that could be the result of dividing a positive number by a negative number. So you might see, here's the way it's written, saying the whole fraction is negative. But that could be from a negative 3 divided by a positive 4. That's an equivalent expression. Or a positive 3 divided by a negative 4. That is an equivalent expression. Now, we don't usually see it this way quite as often with that negative all by itself in the denominator. So you might just, it's okay, all right? It's not quite as common to see it that way. That means the same thing, right? Positive divided by negative, and you got an overall negative result. Boom. How about some messier things like all right, here's a fraction that has more complicated expressions in both the numerator and the denominator than just those simple individual whole numbers. Here's where you have to remember that the fraction bar really is a grouping symbol. You want to simplify the numerator as much as possible before doing anything with the denominator, and vice versa. Simplify the denominator as much as possible. What I want to point out is this isn't just a bunch of multiplications in a row. There's pluses and minuses in the middle of those expressions. So in particular, these aren't just factors, common factors. I can't cancel these sixes. Like here's the 6 in this one and the 6 in that one. Or even between these, 2 here and 2 here, because that's not really the final value. Hard to come up with the easy explanation for that. But until everything is a bunch of multiplied pieces, then you can't cancel anything. So really you need to simplify both parts first, separately. So what am I going to get here? That's a 72 plus a 46. Uh-oh, where's my calculator? That's a 30 minus an 18. All right, I'm going to just work. You notice the sort of preferred presentation format is to do one step at a time, working vertically, and I've tried to model that most of the time. Sometimes, just because of my limited space, I'll go horizontally a little bit more, like right now. 6 and 2 is 8. I think that's 118. You can double check your calculator if you want, but I'm pretty sure that's it. And 30 minus 18, 12. All right, so now that's the result of just simplifying numerator and denominator. And now I'm going to start looking for common factors. Nothing real obvious right now except 2's. I'm going to divide them both by 2, okay? So dividing this by 2, 59. You know, if you have to do this because you're not quite sure, do that. Yes, 59 over 6. Now, let's see. 2 and 3 are the only factors of 6. 2, that's not an even number. 2 is not going to go in there. 3, well, 60 would be a 3. 60 is not going to go in there. Do you know the divisibility trick for 3's? That was one of those things that would have been talked about in section 1.1. How can I just look at that and pretty easily figure out it's divisible by 3 or not? If you can add the digits, the 5 plus 9, if they add up to a number that is divisible by 3, that means 59 would have been divisible by 3. 9 plus 5 is 14. 14 is not divisible by 3. I had kind of figured it out already back here. 8, 9, 10. 10 is not divisible by 3, so I'm not going to be able to divide it by 3. That's a really useful one. You know, we recognize even numbers, multiples of 5s, multiples of 10s, but knowing how to check if it's divisible by 3, that's a very useful divisibility test. Anyway, the point was really here, simplify the top and the bottom as much as possible. I remember there's actually one of the hand-in homework problems is similar. It's got some exponents on plus minus pieces on the top and the bottom. You have to simplify the numerator first, simplify the denominator first, then try to simplify overall. Well, that's kind of all the details there. And we're just about out of time, so pretty good timing there. Any questions right now before I wrap it up for today? Yeah. How about, I'm looking at your nods out there. Is this mostly still review for you guys? You know, you can just say yes, 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 or no, no, no. Not really. Okay, I see some people saying no and some saying yes. So although this is called, like the chapter is called Foundations, intended to, set our framework and hopefully a fair amount of review in there. It isn't always. So that's why we go through every detail as much as we can, step by step. All right, folks, well, we did 1.4 was just the multiplying and dividing of integers, and we did most of 1.5. I'll be sure to start with some extra practice here with this tomorrow, and then we'll get into adding and subtracting fractions and have most of our session tomorrow available for that. So, just want to be as thorough as possible, and then you're trying to get through all those sections, including those 5 hand-in problems, by midnight Monday night. If you get, in particular, the hand-in stuff, done early, I encourage you to try the scanning and sending it to me. See if you run into trouble before, 5 o'clock Monday night, nothing like that, so I can help if possible. All right. Okay, well, that'll wrap it up for today, and see you guys tomorrow, and good luck. All right. So here we go.
Thanks, Steve.
Thanks. Yeah, gonna end.